Today, I'm very happy to talk about the Space Shuttle Main Engine SSME, officially designated the RS-25. SSME is one of the most advanced and efficient liquid-fueled rocket engines ever developed. Designed and built by Rocketdyne, NASA, it served as the primary propulsion system for the Space Shuttle orbiter during ascent. The SSME stands as a milestone in propulsion engineering, combining high performance, reusability, and precise thrust control. It played a central role in enabling 30 years of shuttle operations and continues to support human deep space exploration. So let's take a look at this unique engine. Now, first of all, a little bit history about SSME. In May 1972, Rocket authorized to begin development of engines to be used for space shuttle. 1 year contract and item specification released. And in 1974, that was the year mostly for materials and component development. The first engine testing was conducted in 1975, and in that year, 19 engine tests spanning 23 weeks and 8 TPA to be successfully reached first 2 seconds of engine run. The following year, additional 18 tests in 12 weeks and 5 TPAs to reach 5 seconds. Okay. In 1977, that's when the first engine test at RPL. And in 1981, that's the STS-1, the first orbital space flight of NASA's Space Shuttle program. So this is the history of SSME development. So let's take a look at some specifications of SSME. It utilized cryogenic oxygen, hydrogen as oxidizer and fuel, and the rated power is around 500,000 pound force. Chamber pressure is about 3,000 psi, which translates to about 200 bar, and very, very high pressure in the thrust chamber. Specific impulse at altitude is 452 seconds. Now weight is about a little over 7,000 pounds. Shuttle Main Engine is known as one of the most powerful rocket engines which operated on what we call staged combustion cycle. So this is one of the most important liquid rocket cycles. Now what exactly does that mean? Well, think about the pressure in the rocket thrust chamber here is 200 bar. It's extremely high. Think about if you need to pump cryogenic fuel and oxidizer into the thrust chamber, it requires enormous power, right? So this is where a pre-burner for both fuel and oxidizer come into place. So liquid hydrogen is introduced into a fuel-rich pre-burner, in which actually the power used to drive a hydrogen pump. Similarly, liquid oxygen introduced into the fuel-rich pre-burner and then drives the oxygen pump. Okay, notice that for this pre-burner, only a small quantity of oxygen is used. Okay, so what pre-burners and pumps and the leftover fuel will be fed into the rocket engine plus the leftover oxygen. Okay, so basically at turbine exit, it's quite fuel rich back to the combustor. Some interesting perspective about SSME. I want to compare to jet engines that we're familiar with. For example, the rocket thrust chamber operates at 3,000 psi and has a thrust-to-weight ratio about 75. As comparison, the GE F414 gas turbine engine operates at a pressure ratio of about 30 and has a thrust-to-weight ratio of only 10. Also, as I mentioned, that The preburners are used to drive the turbo pumps, very, very powerful. These high-pressure turbo pump rotates at the speed of 37,000 revolutions per minute, okay? And typical gas turbine engines runs at about 8,000 RPM. So that's almost 4 to 5 times faster than a gas turbine engine. So here again, this is a better sketch of the fuel preburner and the oxidizer preburner, and each burner used to drive the high pressure fuel turbo pump and the high pressure oxidizer turbo pump. Basically, they were able to pump oxidizing fuel into the combustion chamber. Inside the entire engine, the temperature varies significantly, okay? So this greater temperature extremes is more than any mechanical system in common use today. The lowest temperature is where liquid hydrogen fuel is stored at negative 423 degrees Fahrenheit. When the hydrogen is burned with liquid oxygen in the combustor, the temperature in the combustion chamber can reach as high as 6,000 degrees Fahrenheit, higher than the boiling point of iron. So most metal will melt. So this kind of gives you an idea about the extreme environment, the extreme challenges of materials for the SSME. In terms of power, the energy of the 3 SSME engine released is equivalent to the output of 23 Hoover dams. Many of us have probably visited Hoover dams in Nevada. So the power of the 3 engine is 23 times. Okay. This is much, much larger than any automotive or even jet engine power. The SSME high-pressure fuel turbo pump generates about 100 horsepower for each pound of its weight. Okay? And for automotive engine, generates about half horsepower for each pound of its weight. So you can see how powerful that is. And lastly, I want to give you an idea about how fast these pump needs to be in, pumping the liquid fuel and oxidizer. Let's say if we replace the fuel with water and then pumped by the engine, the average home swimming pool could be filled in 25 seconds. That is how fast that the liquid is pumped into the thrust chamber. Okay. I want to show you the very interesting plume out of the SSME. Okay, so this is an image from NASA. At the testing stand when engineers were testing the SSME. Now you can see here, this is the exit of the nozzle. Now at the testing condition on ground, this is what we call overexpanded flow, where the pressure at nozzle exit is actually lower than the ambient pressure. So this is typically on ground testing or at low altitude where the ambient pressure is higher. The flow pattern is called overexpanded. It's kind of like the name suggested, just overexpand takes longer time. So what happens, you see here, the first visible part of the plume, as shown here, this is actually the first shock diamond. Essentially because there's a standing wave sitting there in the overexpanded supersonic exhaust. And there are multiple such diamonds all along the way downstream the plume. To summarize, the SSME represents a convergence of high performance, reusability, and precision engineering, 3 pillars that continue to define the future of aerospace propulsion.